Hello, everyone. I'm Huanchen. I'm currently an assistant professor at Tsinghua University in China. It's my great honor to get a chance here to introduce to you my PhD dissertation completed at Carnegie Mellon. Now, it's quite a challenge to present a full thesis in 12 minutes, so I'm going to mainly focus on describing the high-level problems and the overall structure of my dissertation with a little bit of deep dive into the technical details. And I hope you can use this video as a tour guide to explore my thesis in further detail. So in one sentence, my thesis was about how to reduce the size of in-memory search trees in a database without compromising its query performance. And in many cases, actually improving the end-to-end system performance in addition to the memory saving. So we observed this problem back in 2015 when running the TPCC benchmark on the HStore, which is the main memory OLTP database. And we found in the experiment that the indexes, which are B+ trees, can take more than half of the database memory. That means in many cases, these search trees are literally larger than the data you stored. And someone may argue that DRAM is getting cheap, just don't worry about it. But that's not true. If you compare the per gigabyte cost between DRAM and SSD for the past 7-8 years, the price gap between them is increasing. And today, an Amazon EC2 machine optimized for database workloads typically has a memory to storage ratio less than 1 to 30. So the truth is that DRAM is getting more and more expensive compared to storage. And as the data size grows exponentially, we, as database developers, are facing an even more constrained memory budget. So under this background, reducing the memory footprint of the search tree indexes makes a lot of sense. It improves the memory efficiency of the database system, and better memory efficiency eventually translates to better performance and a smaller bill. Now, when I talk about compressing indexes, people usually think of using general purpose block compression algorithms such as Snappy, LZ4, and ZStandard at a page level or even at a larger granularity. This approach works pretty well for disk-based indexes because it minimizes data movement between disk and memory, and the I/O latency sort of hides everything. But in the case of in-memory search trees, where we're talking about several million index operations per second, the decompression overhead of these algorithms is just too expensive. So basically, existing search tree structures fall into two categories. Performance-optimized trees consume a lot of space to guarantee fast queries, while existing compressed trees require a lot of computation to achieve the level of memory efficiency. Now, the goal of my thesis is to achieve a Pareto improvement over the state-of-the-art solutions by developing new data structures and techniques that can bring us the best of both worlds. And we develop a 3-step recipe for achieving that goal. Now, as the first step, we focus on static data structures because they are relatively easier to compress. Here, we temporarily sacrifice the performance of dynamic operations such as inserts and updates so that we can achieve space that is close to the theoretical minimum. So the main thing we do here is that we borrowed the concept of succinct data structures from the theory world and sort of reinvented this technique from a system engineering perspective so that it's not only small, but also fast enough to be used in practice. Now, for example, this is the basic encoding of our fast succinct trie. Basically, we traverse the trie in breadth-first order and encode it using these 3 vectors. Now, the first vector is just a byte string that records all the branch labels. And the second one, haschild, is a bit vector to indicate whether a branch points to an internal node or a leaf node. For example, this branch A points to an internal node, so we write 1 here. On the other hand, the branch D points to a leaf node, so we put 0 instead. Okay? Now, the third vector structure is also a bit vector, but to indicate node boundaries. Specifically, if a branch is the first branch of a node, we write down 1, like in this branch D. Otherwise, we write down 0, as with this branch I. So basically, we represent the degree of each node using the unary code here. Okay, so with this succinct encoding, we only require 10 bits per node to represent a trie. So 8 bits for label, 1 bit for hash child, and 1 bit for structure. And as a reference, the information theoretical lower bound for tries with a fan out of 256 is approximately 9.4 bits per node. So we're actually pretty close to the optimal. Now to search this encoded trie, we rely on two primitive operations on bit vectors. They're called rank and select. A rank counts the number of ones up to position I, while select is the dual of rank that returns the position of the ith one in the bit vector. Now, because rank and select can be performed very fast in constant time with lookup tables, we can navigate the trie using rank and select efficiently. Here's the formula for moving to the child node. For example, suppose we are right here at position 1. We first compute rank 1 on hash child. Because there are 2 ones up to this position, the result of this rank is 2. Plus 1 is 3. Now we compute select 3 on structure. We found that the third set bit in structure is at position 5, and boom, we have successfully moved to the child node, like magic. Now with this basic encoding, we have also carried out a lot of performance optimizations, including SIMD and memory prefetching, so that the performance of fast succinct trie is competitive to some of the fastest in-memory search trees out there. Based on this novel succinct trie, we built SURF, which is the very first general-purpose range filter that is small and fast enough to be useful in practice. You can think of SURF as a Bloom filter that can also filter ranges. When SURF is integrated into RocksDB, we observed up to 5x speedup for range queries. SURF has won best paper at SIGMOD, and it has since been picked up by many large internet companies. There are also high-quality follow-up work like Rosetta trying to address SURF's limitations, and I think it's still a fun and important problem to keep working on. Okay, back to our recipe. After the first step, we've got these super fast and compact static trees. The next step, obviously, is to relax the constraint of being read-only. And here we introduce the hybrid index design as an efficient way to handle individual inserts, updates, and deletes to the static tree. Now, the key idea is very simple. We put a small dynamic tree as a write buffer in front of the static one, and we do periodical merge between them. And with a clever merge strategy, we managed to amortize the performance overhead of this extra merge step. Now, the last step in our recipe deals with the index keys, because as the first 2 steps really pushed the structural overhead of an in-memory search tree to the minimum, we observe that the actual keys, especially string keys, start to dominate the space. There are 2 main challenges of compressing index keys. The first is that you don't know all the keys beforehand. So our compressor must be able to encode an arbitrary key it has never seen before. And we call this property dictionary completeness. The second challenge is that the encodings must be order preserving. Otherwise, you won't be able to perform meaningful range queries on the tree. So we solve both challenges in this last piece in my dissertation. And the key idea is the string access model. Specifically, we lay out all possible source strings on a single axis in lexicographical order. And we then divide the string access into consecutive and disjoint intervals, close on the left and open on the right. Each interval must have a non-empty common prefix shared by all the included strings. And this common prefix becomes the dictionary symbol of this interval. Finally, we assign order-preserving prefix codes, such as the Hu-Tucker codes, to these intervals based on their probability of being accessed during the encoding process to achieve compression. And now we can use this divided string access to encode arbitrary keys. For example, suppose we want to encode the word academic. First, we locate the word on the string axis, and we find that academic falls into the first interval here. What we do next is to replace the interval symbol AC in academic with the corresponding code 01. Then we move on to the remaining suffix Adamic. Now Adamic belongs to the third interval here, so we replace the symbol ADE with code 110. And this process continues until we reach the end of the string. And you can refer to my thesis to see why this compression model is both dictionary complete and auto-preserving. Now, based on the string access model, we built a super fast compression tool called Hope that can encode arbitrary input strings while preserving their original order. And we found that Hope allows common in-memory indexes such as B+ trees and tries to be up to 30% smaller and 40% faster at the same time. So altogether, from building fast static search trees with optimal space to supporting dynamic operations on these trees with amortized cost, then to the auto-preserving index key compression. These three steps form a practical recipe for achieving memory efficiency for search trees in databases. And that is my dissertation. I would like to thank the big four of my advising team: Dave, my advisor; Andy, the street fighter; Michael, and Kim. This thesis would not have been possible without them, let alone winning the award. Thank you, and very grateful.